Great. Well, it looks like we've got most people on now. So welcome to the event. I'll keep letting people in who might be late over the next few minutes. So if anyone's got any friends who know are coming in, tell them not to worry. But yeah, thanks everyone for joining. Welcome to Night Skyline in London. I'm Rory from Oliver Bernard. And obviously, as you know, we're joined by Katarina and Ivan from Memgraph this evening. So thanks all for coming. It's been our first event in a while actually tonight. So actually really looking forward to it. Couple of things before we start. I am recording this event, so it'll be going out. We'll be sending it out definitely before the weekend, either tomorrow or Friday. So everyone will have that. In terms of questions and things, we'll have some time for Q&A at the end. If anyone's got any particular questions that come up during the event, just put them in the chat function here. I can read them out when there's a gap in the presentation, easier than sort of everyone speaking at once. But yeah, apart from that, I say, so we'll Memgraph tonight. Katarina and Ivan will be speaking through graph-based stream processing in Python. Got quite a lot of interesting things to cover and speaking basically all around that area of technology. So yeah, that's it from me. I'll hand over to you guys now.
Okay, thank you for the warm introduction. So hi again, my name is Ivan, and with me is my colleague Katarina. Today we're going to talk about graph-based stream processing, a somewhat advanced field, but we'll try to cover it in the most basic terms as possible. We actually developed a demo application that we're also going to show you the architecture behind it, the ideas that went into it, so you can get a basic overview of the whole field and the standard development process in it. As you already heard, you can ask questions in the chat, and if you're going too fast, too slow, any kind of feedback is also appreciated. So let's dive right in.
Okay, so it's me first. So I'm Katarina. I'm developer relations engineer at Memgraph. I was born at Croatian coast in a little town of Šibenik. You probably haven't heard of it, but that's fine. I did my master's in mathematics and computer science at the Faculty of Science in Zagreb. And I love to travel, cook, eat tasty food. And here I'm asking for new followers. I'm just kidding. But yeah, you have my Linktree. You can check out my socials. You can follow me, ask me whatever you want after the meetup, whenever. And yeah, that's me. Ivan, you can go on.
Okay, so this is me. I shamelessly copy-pasted a few things from Katarina's slide. I also love to travel and cook, but unlike her, I watch way too much Netflix, and you can substitute it with Amazon or HBO. The statement still holds true. I got my master's in computer science, also in Zagreb, from the Faculty of Electrical Engineering and Computing. And I work at Memgraph as well, a graph analytics company. My role is also developer relations engineer. If you're not familiar with it, we are kind of the bridge between the developers and the product and development team and the company. We try to gather as much feedback, user requests, report bugs. We create demo applications, code snippets, anything that can help developers jumpstart their development process and get to their solution faster. And we kind of also spread awareness about the whole graph technology sector, all the new emerging cool technologies. So this is also one of the reasons why we are here, to spread awareness about this whole new emerging field. Okay.
Great. Let me check whether my controlling your screen works. So just a second. Okay. So first, let me tell you a bit about the graph data model. I'm not sure how well you are with this term. So what are actually graphs? What is graph data model? So here on the photo, you can notice the image on the right. This is actually the photo of the graph. So it's not the graph of a function that you are maybe used to see, but it's a labeled property graph model. So here you can notice that it consists of nodes. So nodes are these circles labeled with person or city or location. And you can notice also relationships between them. So these are the connections between different kinds of nodes. So here, each node can have different set of properties. These properties are key value pairs. So here, for example, we have a property name on each person. And also not only nodes can have properties, but also relationships can have properties. So here, for example, one person can be married to another person. And then you have a property called wedding date. And you can also have not only one property on the relationship, you can have as many properties as you like. So yeah, I think that's it for the basic knowledge of how the graph actually looks like. Next, you are maybe more familiar with the term of relational databases. You have maybe used it. I would be really happy if you told us later on if you use maybe graph databases. That would be a really good thing to hear if you have used them and what was the use case. But relational databases are more popular. They are widely used, but it's not the same. It depends on the data which you have, which database you're going to use. So for example, in relational database, you have tables, and these tables are not connected. In order to connect data from one table to another, you have to join different tables and figure out complex queries which you are going to do upon these tables to receive some kind of insight from that data. But in graph databases, your data is already connected. So it's easier to query it when you have some kind of data that it's, for example, many-to-many relationships. Let's say you have someone who is friends with someone and that person is friends with someone. So you have a relationship that's transitional. Then it's better to use graph databases, since in the relational databases, you have to join different kinds of tables and that query becomes too complicated. Also, a big difference between those two is that in the relational databases, you have a schema which is set, you can't change it, but in graph databases, you can change that. Also, another difference is that in the property graphs, you have properties which can vary from one object to another. So you don't have to have the same properties for the same type of node. So these are the main differences, but it depends on the use case you have. It's not always better to use graph database. I mean, relational databases are really widely used, but we will show you why somewhere in some use cases, graph databases are really a good example of improving your queries and doing your calculations much faster. So how we are actually communicating with the graph database, you are probably familiar with the SQL for relational databases, but with the graph databases, we are communicating using the Cypher query language. It is most widely adopted open query language for property graph databases. So it has clauses such match, delete, set, return. That's something similar to, select, join, something you are used to in SQL. It has functions and also custom procedures, which you can write in Python, C, C++, and Rust. So as I mentioned, SQL is for relational databases, Cypher is for graph databases. Here you can see example how in recommendation systems are a really good example and use case of graph databases, because here you are doing a simple recommendation with Cypher query. You can notice that it's just like a couple of lines in Cypher, while in SQL you have this whole section of text. So on the left, we are actually matching a pattern that we want. So we want a customer that bought some product, which is already being bought by some other customer, and we are looking for the products that the other customer also bought. So that's actually some kind of simple recommendation. And in SQL, you first have to join different kinds of tables, selecting them, and then doing the recommendation. That's why there are so many lines. So this is a good example where graph databases are better than relational databases. Okay, so Ivan, you can go.
We need to cover the topic of graph analytics, so sometimes also called network analysis in academic circles. It's about generating insights that are hidden in the network structure of a graph. So in layman's terms, it means we are analyzing the relationships among entities and trying to extract information from these relationships. How do we do that? There are tons of different algorithms, graph algorithms, that can help us get this information out of the network. I'm gonna talk about a few of them throughout some simple use cases where graph databases are widely adopted. Just some more proof about it. If you ever search for something on Google, you have been using graph analytics because Google implemented the PageRank algorithm, which assigns importance to web pages based on their position in the network and number of connections this site has to other sites. Facebook uses community detection algorithms to find a social circle you belong to and then maybe have better recommendations on what people you would like to be friends with. Amazon uses collaborative filtering to drive up sales. They create recommendations in real time. For example, the Cypher query that Katarina showed you is a very simple example of that. And Pinterest and Uber Eats are pretty good examples of applied graph machine learning algorithms, which can also be used to create recommendations, to predict where links could exist in the network, and so on. So there are quite a few companies that are already utilizing graph analytics in day-to-day life. So one very famous example for graph analytics are social networks, a network of users that are connected with different types of relationships. Here you can see that all of the users are connected with the same relationship friends with. What we can run here are community detection algorithms where we try to find highly densely connected clusters of users. Then we can maybe target them with the same ads. We can recommend other users as friends to them. Maybe they're sharing the same interests because they are part of the same group. This is a pretty cool picture. It's actually a black background. And the reason you can see the outline of the world is because only the relationships among Facebook users are visualized. Kind of makes sense that the Amazon rainforest and Sahara are a bit blurred out, and larger parts of China and Russia because they don't use Facebook as much. Recommendation engines are also a cool use case for graph analytics. As you already saw, the recommendation query, you can also use it here in this data set, which depicts recommendations of movies by users. We can see the movies that a user rated well, which genre do they belong to, and then we find other relationships to the same genre. We can see if a user is connected to other users and then maybe find their preferences to also recommend. There are quite a lot of things that are much more intuitive here in this network than it will be when you were dealing with tables. Supply chain management is also a good example. Here we can do weak link detection to find which part of the supply chain will be prone to troubles. Where do we need to add some redundancy to make sure that the chain will never break? This is a pretty good example of business risk analysis using graph algorithms. Fraud detection is actually maybe even the most famous use case for graph analytics. A lot of companies, either in the insurance space or the credit card space, are doing graph analytics to find fraudsters. You can use simple graph traversals to find everyone who is associated with someone who committed a fraud. You can find all of the cards that interacted with a device that reported a fraud as well. It kind of gets much simpler when you're using graphs. And you can also do community detection algorithms to find clusters of fraudsters. There are a lot of applications. So all of these algorithms I just mentioned and these use cases kind of fall under the umbrella of graph analytics. Some that we didn't mention are BFS and DFS, so breadth first search and depth first search. The shortest path algorithms like Dijkstra's algorithm. There are many algorithms that are just part of the basics of computer science, and they are from the graph space.
Okay, so let me just check the controlling of the screen. Okay, so we are going to jump in to explaining what we used in our demo. So here we use Memgraph as a platform for graph computational streaming data powered by Memgraph database. So if you are also working on some kind of demo, we are talking about graph stream processing. You don't have to necessarily use Memgraph. Here we use it, of course, because we work here, and also because it's tailored for, oh, just a second, someone is, okay. So it is tailored for stream processing in real time, and we are doing this here. So it's also, I would say, very suitable for this kind of example. And it is used to store graph data in memory, run graph analytics, and analyze streaming data. So when you see this kind of term like graph computation on streaming data, that can be a bit of complicated, but actually it's not that complicated. So we have a memgraph, which is also a graph database, and also a stream processing engine where you do different kind of computation on your data, and that data is coming in real time. So that's actually what this means. Okay, so Memgraph, as I said, is not only a graph database, it has this whole ecosystem around it. And maybe the most important part for you would be something that involves Python. So as you can see on the right, on the right of this little puzzle, there are different drivers for different programming languages, and you have Python there too. And also on the bottom, you can see MAGE. So MAGE actually stands for Memgraph Advanced Graph Extensions. And this MAGE is our little wizard. It's actually an open source repository. It's a Python library that holds different kind of graph algorithms that Ivan talked about. So we have implementation of those algorithms in different programming languages, such as Python, and also C, C++, and Rust. So if you are keen to contributing to open source, you can always contribute to MAGE. If you also like doing different kinds of research of graph algorithms, then you may find these implementations interesting. You can check them out. There are lots of Python graph algorithms. So when I mentioned that you can connect to the memgraph using Python language, then I'm talking about GQL Alchemy. So it's a fully open source Python library and object graph mapper. What that actually means is, if you are maybe familiar with the SQL Alchemy in the relational databases, then this is like SQL Alchemy, but just for graph databases. So it's a link between graph database objects and Python objects. It has OGM capabilities, query builder. On this storage, this means that you can store some properties to the SQL database when you don't want them in your graph database, so that you can do the calculations faster. And also there is a graph schema validation. So we are currently also developing this library. Ivan and me are also working on it. So it's an open source library. It's a Python library. So also if you are keen to open source contributing, you can contribute to GQL Alchemy. Okay, that's it.
So before we dive into the application, let's consider the data set that we used, that we analyzed. In the end, it was around the holidays that we did it. So the idea was to scrape Twitter for certain tweets, and we decided on the ones that had a hashtag Christmas in them, because it was that time of the year. And there was a lot of buzz about it. And we wanted to see which users on Twitter were the most influential ones and had the largest communities around them. So what we did, we scraped all of the users who in a certain time span used the hashtag Christmas. We saw who was retweeting each other. We constructed a network from it. And then we decided we will run the PageRank algorithm to calculate the most influential user in the network. And we'll use a community detection algorithm to find communities of users who were retweeting each other. Why does it say dynamic PageRank and dynamic community detection? Because when you have a large network, it will take a lot of time for one algorithm to run through everything. For example, if you have 1 million nodes and edges and you run the PageRank algorithm, it will take a few minutes. And if you're doing it every single second or even less, whenever a new tweet arrives, this just isn't feasible. So we have dynamic implementations of algorithms that only recalculate for parts of the network that are essential for the new information that's coming in. So they are done in a fraction of the time. They take up less computational resources, and it's just much better for the whole stream processing part when it's done faster. So this is literally the model of the dataset, is as simple as it can get. There are only nodes of the type user in the database. So a lot of users who are connected with relationships of the type retweeted. So whenever one user retweets another, a relationship between them is created. And there is only one property in the whole database at the beginning, and that's username. So the username of the Twitter user. Later on, two additional properties are added to the data model. One is rank, which indicates the PageRank value once it's calculated, and the other is cluster, which indicates to which community that user belongs to. For example, all the users who have the cluster 1 belong to the same community, all users who have the cluster 2 belong to the same community, and so on.
Okay, so we already mentioned something about streaming, graph computation on real-time data. So actually that's graph stream processing. We are going to analyze the data that comes in real time instead of batches. So how that actually looks like, you have input data, and that data goes into the stream processing engine. So for example, Memgraph here is actually doing the role of stream processing engine. In the stream processing engine, you are doing different kind of graph analytics on the data that comes in real time. So like Ivan mentioned, you are doing the dynamic PageRank, dynamic community detection, something similar to that. I mean, you can do traditional algorithms, but it's much slower. And then after that, your new calculations are going to the output, and you can do different kinds of analytic on that output. You can gain really valuable insights to your data, or you can give it to another output stream that is going somewhere else. So this is actually what makes whole graph stream processing. So it's a type of big data architecture in which the data is analyzed in real time, like I already said, and it's used whenever you need to extract some kind of additional information from your data as it's being consumed. And all this process is happening asynchronously, so the data source and the stream processing are working independently without waiting for response from one another, and that's a really important thing.
Okay. So let's look at the architecture of the app that we built. Pretty simple. At the beginning, we have a data source as always. And as I already mentioned, ours is scraped tweets. Sorry. Normally, we will connect to Twitter through their API and do this in real time and wait for tweets to arrive, but we couldn't bet that at a certain point enough users will tweet about something, include some hashtag. So we did that beforehand. We scraped during the holidays. We created a CSV file with lots of data, and now we are kind of mimicking this real-time behavior where a Python script sends a message each second to our Kafka cluster. So we are just mimicking the tweets coming in real time, but that's okay for the purposes of our demo. So now that we have messages arriving into Kafka, that is our message broker, but it can also be substituted with Apache Pulsar, with Redpanda, RabbitMQ, anything else that can just fit into this synchronous architecture. So tweets are coming into Kafka, and then they are sent to the stream processing engine, which is Memgraph in this case. So once a message arrives here, we do some calculations, we run some algorithm, extract the info we need. And then what we do is we send that data back to a Kafka topic. Everything happens asynchronously. And then we can consume from that Kafka topic in our Python Flask server, which is essentially the backend of our application. We have an endless while loop here that's waiting for messages from that topic, and whenever a new one arrives, it's sent via a WebSocket connection to our front-end client that was created in React, and we use the D3.js library for graph visualizations in real time as well. So now it's demo time. Bear with me for a few seconds because I need to start everything up.
See, you have already opened the React app.
Yes, already prepared. So what's happening now in the background is I'm using Docker and Docker Compose to start up all the services. For example, Stream 1 is the Python script that's going to send messages to Kafka every second. This is the Kafka server. This is Memgraph, the stream processing engine. This is Zookeeper, something that Kafka needs to use. And I'm also gonna fire up the, okay, let's remove this, the front-end client. It also needs a few seconds to build because it's a React app. You can thank Kate for that.
So if it doesn't work, it's my fault, that's fine.
Yeah, I think it will definitely work. So what will happen is nothing's gonna start streaming messages until the first request is sent from the client to the backend server. So I need to refresh this. And now the first request has been sent. And yeah, messages are being produced. As you can see, this is, for example, a typical message where you have a username. And here is the rank that was calculated as the message was ingested in our stream processing engine. In the background, you can already see it happening. This is our network being constructed as messages are coming in. For example, let's find something I'm familiar with. Okay, no. The user Derek King 2 is connected to, I can't pronounce this, but you get
God give something like that.
And beneath, you can see the community detection visualization. Here, all the nodes are colored based on what community they belong to. Sometimes it takes a few seconds for them to change their colors accordingly because the community detection algorithm is a propagation-based algorithm that iterates through the network. Yeah, it's pretty cool. And here I forgot to mention the radius of the nodes. It depends on their rank. So this one, the largest node, World Music Award, a pretty influential Twitter user, was retweeted the most times in the network. This is why it's the largest node, because it also has the highest PageRank value. And you can see the nodes changing their values because every time a new node comes into the network, some values need to be recalculated because they either gained or lost influence based on what connections the new node has. So this is more or less it on the demo side. I can return to the presentation and we can go a bit into the technical details that are behind the app.
Okay, so let me tell you a bit what we did here. So first, we needed to create a transformation module. So what that actually does, so Kafka messages are being sent into some kind of topic, and we are reading from that topic. And then Memgraph needs to know what to do. And since we already thought that we are communicating with Memgraph via Cypher query language, Memgraph doesn't understand the messages that are coming in JSON format, for example. So here we are actually translating those JSON messages into the Cypher queries. And we are telling Memgraph, okay, when you receive some kind of message that has source username, target username, you are actually going to start this query, which is creating two users and the relationship between them. So that's a simple transformation module, and this is written in Python. And you are creating this kind of modules whenever you are sending some kind of messages through with some kind of message broker. Next, we need to set everything up for our dynamic algorithms. Here is how we set up the PageRank algorithm, and you are also setting up the community detection algorithm in the same way, a similar way. So here we are creating a trigger. And what we are actually doing is we are setting up the newly calculated rank on the certain node. And whenever that rank is being set up, we are calling, you are seeing here, publisher.update rank. What that actually does, this is a Python script that sends this update, so information about the user and its updated rank, to the Kafka topic. And we are in the backend application waiting for the messages from that topic. So whenever a new PageRank or community detection is being calculated, then you are receiving that message like you saw on the app that Ivan started up. Next, we have to create and start stream. So here you can notice this is all also written in Python, and Memgraph Kafka Stream is actually imported from the GQL Alchemy. You are giving it some kind of properties that are needed. For example, this transfer property is actually the first thing I showed you, the transformation module. It's called twitter.tweet. So you are telling it here how it will translate all the messages that are being received from Kafka, where it's listening, in which topics, and so on. You can then create a stream, and you have to start a stream in order for this to work. And also, we are creating a trigger. I mentioned 2 triggers for PageRank updates and community detection updates, but we also want to create a trigger on every creation of node, old relationship, because we want all updates to be drawn on our front end. So whenever new node comes or whenever new relationship is being created, this trigger will be fired up. And here you can see that we are calling publisher create. That means that there is also another Python script that is sending messages to the retweets topic from which we are reading. So what we did, let me just give a bit of overview of that. So we created transformation module in Python. We run the PageRank and community detection algorithm with GQL Alchemy. We created and started a stream with GQL Alchemy. And we created a trigger and module to set PageRank results back to Kafka topic. Yeah, and this is what you saw in something similar to this in the demo. So this was drawn, like Ivan mentioned, with D3.js. That's a JavaScript visualization library. I mean, it's the application could be a bit, I mean, with React, it could be much prettier, but a lot of effort was put into this real-time visualization. And D3 is actually pretty good if you want to visualize graphs. It's fast and it's well suited for the type of data you have. For example, if you have nodes and relationships, D3 has nodes and links, and then you can draw this all very fast. Okay. And yeah.
That's more or less it from us. The app we created is called Twitter Network Analysis. It's just a basic demo application, but you can visit the GitHub repo. It's under the MIT license, so you can use the code if you need something to jumpstart your own process. Completely free to use. You can also contribute to it. You can always ping us. Our accounts are also here on this repo visible. What we also did is we created a sandbox with the data set that we mentioned. So all the scraped tweets, you don't have to install anything. You can just play with it in the browser to see what the graph looks like, what the connections are. If you want to try out some graph algorithms or traversals, you can play around with it freely. We'll be sure to get a copy of this presentation to you sometime after this meetup, so you can also have access to all of these links. And in the end, if you have any questions for us, anything graph related, anything from the graph technology space, definitely doesn't have to be only about Memgraph. You can join our Discord server and ping us directly. We are always there, always listening, watching out, helping our community members. And here you can also see our Twitter handles and email addresses if you need to connect with us privately. Thank you very much for listening. Thank you very much for joining today. Hope we didn't bore you to death. What else is there to
Great
say?
presentation.
Thanks.
Thanks both. One quick question from Mikael in the chat that just came through. He said, does the entire graph need to fit in the memory? Sorry.
Yes, in this case, we need to fit everything in memory because we need the results as soon as possible. There is no room for delay. So that's why we are utilizing the in-memory architecture.
Yeah, but this on-disk storage from GQL Alchemy is good if you have large properties, which you can save in the SQL database, and then you'll save a bit space in memory. But yeah, and thank you for the comment of the real-time part of the UI. Thanks, means a lot.
Yeah, it was very hard to implement. I saw her do it.
You saw me crying. No. Thank you, Ray.
Anyone else got any questions?
Hi. So I was from the presentation, I found out that you said the project is open source. Is it possible we could get like a link to the GitHub repo so we could check a few things out if that's not going to be a problem?
Did you mean GQL Alchemy or Mage or both? I mean, I can send you both.
Please just send both. I'll just take a look.
Sure.
That'll be cool.
Will do. Okay.
Thanks a lot.
I'll send a variety of links out. Actually, there's someone's put them in the chat actually.
Oh, nice, thanks.
I'll send some links out via the meetup group as well. So everyone here will have it come through to their email as well. So yeah, everyone should have it pretty easily soon.
Great.
Yeah, whoever sent a message, kudos for being the fastest finger.
Yeah.
Thank you.
Oh,
I'm curious.
Nice.
Yeah, always great to hear. I'm curious if anyone here maybe used any graph technologies, graph algorithms in their either research or personally private projects. It's still a new field. It's
yeah. Probably, yeah. But it would be fun. Yeah.
Yeah, just NetworkX, it's a great library, but yeah, I haven't used stuff like full-on graph databases, but I guess a lot of people would have used NetworkX.
Yeah, I also started using NetworkX during my university years. A kind of graph databases evolved from that space. NetworkX is more of an academic Python library. And then a lot of developers saw the need for optimization, some kind of advanced features. And that's probably how the first graph databases were born.
Okay. I've seen GraphQL.
Maybe some overlay in that they both represent a graph structure, but it's completely different use cases. GraphQL is used on the API side and the web of things and so on, whereas Cypher, for example, is only graph database related. There is one graph database that is actually using GraphQL as their main query language. I'm not sure which one.
Is it Tiger Graph? No, I'm not sure.
Maybe dgraph.
I'm not sure, yeah.
But that's the extent of it.
Yeah.
But pretty good question. There is a correlation.
Looks like that might be all the questions. Yeah, well, oh, sorry, one more.
Okay.
Yeah, in your opinion, can Memgraph help with GIS-based apps?
Did we have any good example of something like that?
Not sure what the specific use case is, but a lot of people are using graph structures to map geographical coordinates. For example, I know the engineering team in Memgraph is adding
So the user is
geospatial.
actually asking so to like figure out distances between like locations. Yeah, that is a pretty good use case. For example, we have some kind of use case of Uber-like where you are actually checking the closest drivers and something like that. That is a pretty good use case for graphs. Like you can calculate really fast and also data that is coming in real time. You are calculating all those distances, the closest distances and so on. So mapping out the locations is a pretty good use case, I would say.
Yeah, thank you, Katarina, for stepping in. I already
Sorry,
forgot the most basic use case, and that's like
yeah,
finding path between locations.
I noticed you didn't read the chat, so just to make it a bit easier.
Nice.
No problem, and thanks for the DevRel peeps. I'm also really happy that there are many of us. Usually people don't know what we do, so it's fun to have you here.
I just remembered one use case that we worked on is also trying to find the shortest location between some kinds of drivers and the different entities in a moving network. So yeah, definitely. But pretty slow.
No.
The next talk, we haven't got one booked up yet for Python London, but we have got a potential coming up soon. So hopefully in the next month or so, probably towards the end of April, we should have a few more things going on. Everyone obviously here is on the main meetup page as well. So as soon as it comes out, you get a notification straight away, and yeah, can sign up from there. And yes, the video. So I've been recording the video. It's a good point. So for anyone who was a bit late, I know a few people came in 5-10 minutes late. So the whole thing was recorded from the start. It'll be shared. Yeah, so it'll be uploaded to YouTube, and I'll share a link via the meetup group as well. So that will all come out to your email addresses. So yeah, straight away we'll send you some links for everything to do with this talk. Links to, well, you can see the one here with Discord, the GitHubs, anything to do with the talk. We'll send out those links and then we'll send out the video link in the coming days. It will definitely be out before the weekend, so keep an eye out for that. And yeah, then everyone should have everything from there. As I say, keep an eye on the meetup group. We'll have some coming through soon. But yeah, thanks a lot, guys. Really interesting talk today. Really good questions as well, which shows that certainly everyone was listening and everyone was very interested. So thanks very much.
Thank you for having us.
Yeah, thank you all. Thank you for having us. And
thank you very much.
Hvala.
Hvala.
Great. Thanks,
Best
everyone.
Question.
Thank you.
Have a great evening, and yeah, see you all soon.
You too.
Bye.
Bye.
Bye.